Industrialization, urbanization, and transportation has attempted to have a place that overlaps, and many times the overlap isn't good. When those results turn negative, they can be covered up or disregarded as a result of a concern that can cost jobs, leaving those who appear to be the messenger of the bad news as the concern for their negative observations. Yet the negative observations can be documented, while research as to where they lived, where went to school can produce a timeline that can be utilized as the advocate to help those who have either existed, either past or present, in these areas. President Eisenhower told Americans to be aware of the military-industrial complex, and this podcast is definitely an example as to why that is the case. On this podcast is two people who are bringing the attention of the concerns of the environmental impacts on living in the flight path of major airports in the United States. Today, I'm happy to speak with Senior Directors of Flight Pattern Kids, Patrick DeFeo, and Dr. Mark L Witten, who serves as Science Advisor for Flight Pattern Kids and the author of the book Jet Fuel Toxicology, a study of the effects of jet fuel and its applications. And again, I want to thank Patrick and Dr. Witten for joining this podcast today. How did the two of you get together in this project?
We were introduced.
Well, it's been about 10 to 12 years we've been working on this effort. I don't even remember, Pat. I think it was the people at Santa Monica Airport.
Yeah. You had just visited Santa Monica, and they were talking about the problem. And I believe you went down and you met Virginia there.
Yes, I went to the LA Pen Show because I collect pens and stuff, and I took a day off and went down to Santa Monica to observe the problems in the air pollution there from that airport, and then they knew you, and that's how we made the connection.
Exactly, and so we set up a meeting between some of the people we had up at SeaTac at the time that were helping me out, and then some activists down there at Santa Monica, and then Mark and I. And we discussed, what we've done in the past and our experience in this and that. And we just hit it off. I believe it was at that meeting when we decided we were going to work together on this. And, the rest is kind of history now. It was about 11 years ago, I think now, Mark. This is our 11th year.
Yeah. I remember going to my uncle's 90th birthday party in 2014 in New Mexico, and telling one of my relatives that I was working with the Seattle group. So that's at least 10 years. So yeah, it's at least a 10 to 11 years.
And one of the things that we wanted to do was to prove this beyond a reasonable doubt, using science, using many methods, different scientific methods to bring all of the evidence together. And then we developed systems and processes, involving link analysis and stuff to read all of this data. One of the other things that we did is we brought DNA into this, which has never been done before. So Mark and I were really excited about doing this for the first time ever. It's never been done before. And so that worked out.
And what really helped us was, the human genome wasn't even mapped until the early 2000s. And so a lot of this DNA stuff was very immature, and as this project started, it became much better, and so Pat incorporated that into our analysis, and so we can now go down to the genetic level and look at all the changes in the genetics from exposure to jet fuel emissions.
It's good stuff because one of the things it does for us, it gives us positive proof in many different ways. One of the ways, is just one example, is, there's a question, okay, a person lives around SeaTac Airport all their life. They're conceived, born, and raised around SeaTac Airport, and they get cancer, okay? Well, was that cancer familial? Is this something that everybody in the family has, that mom passed the genes, or dad passed the genes, or even grandma or grandpa passed the genes? And we can definitively establish where those mutations that caused their cancer or that type of thing, where they came from, whether it was familial or whether it was environmental. And we do that by looking at the whole family's DNA, mothers, fathers, and let's say brothers and sisters. And by doing that, we can see, did it come from mom or dad? No, it didn't. And your only other option, it came from the environment type of thing. And so it leaves markers behind also. in the form of DNA double-strand breaks, which lead to indels, insertions and deletions. So when the DNA goes to recombine, when it goes to fix itself, it does it incorrectly, and a mutation can form there. And off of that, easily cancer or an autoimmune disease can be started just by that. And so,
Tim, this is how sensitive the body is. You have about 37 trillion cells in your body, and they're constantly turning over. Like you get a new set of skin cells every month or so, and same with immune cells and this type of thing, and hair. But all it takes is maybe of the 3 billion base pairs in the DNA double helix. All it takes is maybe one of those base pairs being broken, or like Pat said, in the repair process, a new base pair is put in there. It's called a single nucleotide polymorphism, a SNP. And maybe just one SNP is enough to initiate a cancer process.
There you go. And we can see that.
Wow.
We can see that in the DNA. It's really cool. Especially one of the things we did also is, we didn't look just at CTAC. If you look at CTAC, that doesn't tell you the whole story, because what's beyond CTAC? So we went beyond CTAC, went down to Santa Monica. We've been over to O'Hare Airport. We did another project in agriculture down there in Imperial, California. So we've dealt in many different environments, all dealing with metal zones and all dealing with the people's health. And when you look at these different areas using either our family health history or our DNA, you can see the differences right away. And you can see how much the environment plays a role in that. More than anything else, the environment plays a role in the illness. What type of environment, what types of toxins that you're exposed to, and the time, the length of your exposure. And a critical factor that we find at CTAC is you were conceived, born, and raised around it, you're going to be much worse off than, let's say, somebody that moved into the CTAC area from a clean environment when they were 12 years old. They would have less disease than somebody that was conceived, born, and raised around there. And we show it over and over and over examples of this. We have one family down in Imperial, California. We actually looked at, I think it was 38 family members. So we went real deep into their family health history and that sort of thing. And so you can, it shows a big picture of what's taken place. And, to us, it's longitudinal data too, because with this, we can go back in time, and using the assays, we can also go back in time and see what that child was exposed to, let's say in the womb, right? That if we do that using deciduous teeth, which are baby teeth. We also use baby hair, okay? A lot of folks in Pacific Northwest kept baby hair, the kid's first haircut, take a snip of it, and they'd wrap it up in plastic or whatever and put it away, right? And they'd store that. And they did the same thing with baby teeth. We can actually assay that. We send them over to Mark, he takes them into the lab, we assay that. And we can see what that child was exposed to as it was developing as a fetus, right? What metals it was exposed to.
I have some for you.
Yeah, it's wrapped in the teeth. So that that ended up being really good data to use. And we link all this together. Basically, it's we use, think of a pivot data or something to use a gene alone, and we can link the gene to diseases. We can link the gene to the metals actually, and what effect the metals would have on a particular gene and that sort of thing, and then link the metals to the disease itself. So there's collecting all of this data left us in a position where typically when you get done with a study or an investigation, there's a little disclaimer at the end that more study is needed. We don't have that. We were able to draw the conclusions because we went out and we gathered all the evidence so we can definitively answer the question. And I'm going to turn a little more of that over to Dr. Witten. He can talk about that a little more.
Well, to give you an idea, like I said before, the human genome wasn't even elucidated until 2002, the early 2000s. And everybody was shocked. Oh my God, we have 100,000 proteins in the human body, and they thought that there would be 100,000 genes in the human genome. No, there's only about 22,000. The slugworm has 17,000 total genes. So, but that also brings out this particular problem. you have 22,000 genes that produce 100,000 proteins. So on average, each gene may contribute to making 5 different proteins. So that's how complex the human genome is. Now, over 22 years since it was first elucidated, the human genome, now we have the beginnings of genetic pathways, like Pat was talking about. So we see a gene that's altered from one of the people living in the SeaTac area, and now there's enough data out there and gene banks and this type of thing run by the NIH and this type. So we can now, and companies have now put these genetic pathways together, and Pat's buys the software, and away we go. And so eventually, all of us will have a credit card with our human genome on it. You go to the doctor, you're feeling sick, he will make a diagnosis, then he'll take your genome card, put it into a supercomputer, and it will let him know which drugs will work best against whatever disease you have, and this type of thing. Genetic medicine, we're on the cusp of really having genetic medicine for the first time in human history, where we can then tailor make the drugs that work best for you and this type of thing. And we can also map these people as they get exposed to something at work or whatever, and see how it changes their genome, and have a very good idea whether they will develop cancer down the road or autoimmune disease or this type of thing. That's already beginning to happen. I had my general practitioner do a genome on me, and it predicted that I was moderate risk for 2 diseases, and that was 10 years ago. And guess what? I have both of the diseases now.
Wow.
That's amazing, isn't it? Where we're at.
Yeah.
Totally amazing. Totally amazing.
One of the things that I was brought up to is, and I saw this on one of the news reports in Seattle, you bring the data to an attorney, you have a class action lawsuit, and he's pretty amazed and probably yet overwhelmed with, how many times we talk about AI and how many times we talk about big data nowadays. And, certainly that's something that I do a lot of here in Oregon, about how the negative impacts of it are. And yet here it is showing the big picture of a growing concern that, of how it should work. How do you guys think about that?
Well,
AI is, I've got a biosensor, and I got a grant from the U.S. Department of Agriculture, and I engaged an AI company, and it took the sensitivity and accuracy of my biosensor from 75% to 99%. So that's what AI can do.
AI is a very, very good tool, but let me say this. For litigation, there's not one piece of data that I give to the lawyers, the evidence, that is run through AI. Okay, so there's no algorithms that calculate or do it, minus the labs. Of course, the labs use algorithms. Okay, I use simply hard data. I do not step on the data at all. Okay, that's one of the rules we have. If you get into our database, is your hard data. You have not been stepped on. There's been no algorithms used. No AI has been used whatsoever. Okay, and the reason we do that, Tim, is simply because we cannot have 100% confidence into the outcome, the answers that it'll give us. Okay, and I learned that a while ago because I tried to stuff this through AI and tried to give me an answer. I went to 3 different software companies and I had them take a look at our system, right? And they were totally amazed, by my system. The first thing they told me was AI is not for you. AI is for somebody that does not know their data, where you're getting somebody else's data set, something like that. Somebody's put it together and you're trying to figure out the answers. You simply don't know. We know all the answers. I put all that data in there. I know what the answers are. And like I said, it's all hard data. It's the real thing. It's nothing that's been computed or anything. So in this instance, what happens is I can bring out data and bring you evidence that with 100% confidence. If I was to use AI, that confidence would drop.
Well, because every AI company has different algorithms. And
Exactly
my
right.
AI company for my sensor, they won't tell me those algorithms. I mean, that's because if they
No.
tell me the algorithms, there goes their proprietary technology.
Yeah,
And the
exactly.
bottom line is
And they were
is
shareholders.
that Pat is right. Everything that we have, all these thousands and thousands of data bits, is all on hard data. It's not been run through AI. What I see down the road maybe is once we get this all sorted out, is maybe in other places or whatever, AI could help us predict what's going to happen
Exactly.
around
Yeah,
these other airports. But that's in the future. The bottom
exactly.
line is we know we have a very good idea what's happening at SeaTac Airport. Like with our tree ring study, there just happened to be a park just north of SeaTac with old fir tree growth trees there, and just south of SeaTac. So we send our tree ring expert up there. He goes back in time, Tim, to where we looked at tree rings from 1900 when there were no airplanes
Wow.
anywhere. And then we went to Chicago O'Hare last summer. In fact, it was this weekend. It was Father's Day weekend. I spent Father's Day of 2023 in the Chicago area. We could not find large trees because the Dutch elm disease had wiped those trees out. So we used tree leaves
Wow.
and soil samples, and we found double the amount of metals that we saw at SeaTac because there's 7,000 flights a day into Chicago O'Hare, and there's only 3,500 flights per day into SeaTac. And it was an incredible correlation, wasn't it, Pat?
Oh yeah, absolutely. That was the first thing that just stood out when we looked at the data. So, and I guess it wasn't surprising to us at all.
And you said somewhere in the data too that it wasn't coming from the branches or the leaves, it was coming from the trunks itself. So that would
Well,
imply that it's coming from the
no,
ground.
no.
Okay.
Let's say that differently, Tim. It's
Okay.
here's what happens. And we want to be specific about this because we had some issues with the first lawyers over this, and we want to be really specific on what happens. If once a
Okay.
tree takes it up, let's say we have a Doug fir tree, and once that tree takes it up inside of it, and so Dr. Shepard, he's doing a core, and then he picks that up. That's locked inside that tree. That does not come out. That will
Right.
not go up to the leaves, and that will not go up to the branches. That sort of thing. It stays locked in those tree rings, right? And so, because of that, it's a good thing, right? A natural thing, and in nature, and that sort of thing. You have all these trees that have all this metals locked up. So when we have a big forest fire, you will hear warnings about, hey, this is dangerous. Don't breathe that smoke. It's full of metals and that sort of thing. As one thing. Now, with that said, let's think about this for a minute because the metals are coming from the air. Okay, so let's say it's the airport and they're flying over Sunset Park, like Mark was talking. They did some sampling there. So what happens? These drop down on the trees. Well, they land on the leaves, right? And it lands on the outside of the tree, the bark and that sort of thing. Okay. Now in the fall, the leaves are going to fall off. They're going to blow around. So those metals are going to fall down off of the tree because they're attached to those leaves, and then they're going to blow around and go into a wider area. What's also going to happen is, like we know, we have Seattle, we have a lot of rain, right? So it's going to wash all those metals off of the leaves and off of the branches. Now, anything that drops straight down, where the root rings are, is typically what the tree goes vertical, the root rings. Okay. So anything drops straight down there is a lot of that's going to be picked up by the roots, right? And then taken up into the tree. But if you have a big rain like we get in Seattle all the time, it'll wash it away from those roots. And what it wants to do is wants to take those metals to the lowest point because they're heavy. So gravity's in effect, and it's going to try to wash it to a creek and wash it down lower and try to get it down to the sound, Puget Sound, right? That's where the drainage from Sunset, eventually goes. And so that's how that process works, okay? So anything that gets locked up in the tree doesn't really get released back unless there's a fire. Does that make sense to you?
Yeah, that makes sense.
And then
Absolutely.
in the Chicago area, because we saw a lot of old tree stumps there from Dutch elm trees that were giant trees, but of course the Dutch elm fungus killed them all. And so, yeah, we saw a lot of little maple trees that are maybe 10 years old but that's not going to tell us the story because they're too small to treat core, and so that's why we switched to leaves and soil, and found again the correlation, because you got 7,000 flights a day going into Chicago Air, and this was on a Sunday morning. We're on the west side, the west flight pattern into Chicago Air, and the planes were coming in every minute on a Sunday morning.
Wow, that's incredible.
Yeah, and it never stops, Tim. Yeah, this is one of the reasons that this is a big problem. Let me throw this in there. It's something we haven't really talked about. We use OSHA PELs, okay? Permissible
Exposure limits.
There you go. Exposure limits. The reason we use this is because OSHA has defined this over many years of research and that sort of thing in the workplace, right? And they say that you can only be exposed to this much. If it's this or over, you must be taken out of that workplace. You cannot work there anymore until that clears up. The problem with this, and the problem with anything that we try to follow, right, or try to comp to, is everything looks at more of an acute exposure rather than a chronic exposure, or one-time acute exposure, and then it goes away. And also, they look at one metal or one element, okay? We're talking about, geez, out of 50 of them that we look at least 25 of them that are in the toxic range. So it's metals poisoning. This is not, this is not addressed by OSHA at all. It's not addressed by any model that Washington State Department of Ecology has or EPA has. None of their models address any of these things. Okay.
And Tim, so one of the things that we found is a lot of these aircraft emission metals are known as metalloestrogens. And what they do in the body is they somehow interact with the estrogen receptors. And so that's, now you're changing, especially in women, you're changing a lot of physiological functions because these metals are interfering with the estrogen receptors in the body. And then you have other metals that are known as anti-apoptosis. Such as iron and chromium and this type of thing. What they do is they interfere with the natural cell death process. Like I told you earlier, every month you're turning over enough your entire skin cells, your hair, your immune cells, and now that natural death process of those cells replaced by new cells is being interfered with because the old cells are not dying properly.
Thus comes cancer.
Yeah.
So
how many?
I
was going to say one of the questions that I had was if I looked at the table of the periodic table of elements chart, how many would you say you have found in the research that you've done with the airports and the airplanes?
Oh boy. Okay, I have it listed in the documents. I think you have it there. So I'm going to talk off the top of my head. That's probably about 25, 20 to 25, 15 to 25. I believe that we're focusing on like 22 of them. Mark and I decided to focus on, for the lawsuits and stuff.
But Tim, let me tell you about one of them.
Go ahead.
In the innards of these jet engines, where it's the hottest, where the whole principle of a jet engine, it sucks in a bunch of air, it heats the air expands, it goes out the back, and there's your thrust, and the plane goes forward. Okay, it's the inner part of these jet engines where the temperatures are the highest. They use thorium. Thorium is a radioactive element right next to uranium on the periodic table. Actually, uranium and thorium are 4,000 miles below your feet right now in the center of the Earth. And that is why the nickel iron core of the Earth is molten, which gives us our magnetic field. And just with this aurora borealis, this sunstorm over the last month or whatever, we didn't have that magnetic field up there. All that radiation would eventually kill everybody on Earth. And also, that's why Mars at one time had a bunch of running water, a moderate climate. It lost its magnetic field. and the sun stripped away its atmosphere over the millions of years. And so thorium has a half-life, they think, of 13 billion years. They can't measure it. And so the reason they use it in the innards of these jet engines is because it can withstand those high temperatures and not creep, not expand. But what it does is it flakes off and goes out the back end of the jet engine. And
That's the
now
bad
you're
part.
bringing in an element that's radioactive, but it has a half-life of 13 billion years. It is never going to leave your body. And it's never really going to decay much to where it's always a constant threat.
You understand that? You understand what ROS is and all that type of thing is, Tim, that the metals will actually give off, it creates in your body. And that alone will cause DNA double-strand breaks and the metal itself. So
Reactive oxygen species is what
right.
ROS stands for.
So the reaction will cause a DNA double-strand break, which can lead to cancer, and the metal itself will lead to it. So you get a negative feedback loop there that is horrible. And I drew a diagram of that in the paperwork I sent over to you. It makes it bad.
Yeah, that was one of the interesting things about this too.
Let me throw something in that's really important because it's happening right now and everybody can see it. You know these beautiful orange and red sunsets and sunrises you see every day? What that basically is particulate matter up in the air, right? And it creates these beautiful colors. Some of it could be metal, some of it could be other chemicals, it could be sand, could be radioactive material. They found all sorts of stuff up there. So think about this. An airplane, jet aircraft's going to fly through that at what, 500 miles per hour, 400 miles per hour? What do you think that abrasive does to the paint and the aluminum magnesium skin on the aircraft? Or if it's carbon fiber, it sandblasts it. All that paint's coming off. You've seen recently in the papers and stuff how these airplanes are kind of coming apart, right? Especially the carbon fiber, the new stuff. But the old stuff, basically what's happening is that paint's coming off. And what's in that paint? Barium, cadmium. Underneath it, we have aluminum, magnesium, barium, cadmium. We're all off the charts. Every time that plane flies, it's being sandblasted.
And another thing that contributes to the paint coming off these planes is the change in barometric pressure. Because as the aircraft is at high altitude and then comes down, the fuselage at high altitude expands due to the low barometric pressure. And when it lands, the skin of the plane contracts because of the barometric pressure. So again, the Air Force has developed a way, and of course it's top secret because they don't want anybody else to know it, but aluminum corrosion is a serious, serious issue. That's why they paint the planes, okay? To try to reduce that. Why do you think we have B-52 bombers that are 70 years old that are still flying? Because the Air Force has developed a way to stop that corrosion in the aluminum skin of those airplanes. But of course, they don't want to give it to the commercial aircraft companies because then our enemies will learn that process. So, but the problem is, we found barium all along the flight path into SeaTac Airport.